Hello, hi everyone. Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. I hope you are doing well wherever you are right now. Okay, and so now I will discuss about topic 4 in our subject CS513, which is numerical solution of ordinary differential equations, ODE. So basically this topic have two subtopics, Euler's method and Runge-Kutta method. Okay, as usual, similar to the previous topic, before we go to our main syllabus, I would like to give you some overview or an introduction about what is differential equations or ordinary differential equation. Okay, we can see here, this is called as differential equations when we have an unknown, which is v, and its derivative. Alright, this equation is called as first order equation because the highest derivative that we have is first derivative. If you have second derivative in the equations, then we consider the equation as second order equation. Alright, here v is the dependent variable in the equation, while t is the independent variable. So when we have only one independent variable, that is called as ordinary differential equation. If you have two or more independent variable, that means the equation is a partial differential equation. Okay, a higher order equation can be reduced to be a first order equations. Okay, this can be done. For example, here we have a second order equation, and then by defining a new variables of y equal to dx over dt, then differentiate dy dt equal to d square over x over dt square. So this can be substituted back into that equation to get equation 4.5 here. Okay, or this one if you rearrange. Alright, so equation 4.3 and 4.6 are a pair of first order equations that are equivalent to the original second order equation. If we want to get back the original equation, then we can just rearrange and substitute back the value. Alright. Okay, without computer, ODE or ordinary differential equations are usually solved with analytical integration techniques. For example, here in the equation 4.7 is the integration of equation 4.1, so that we get v equal to integration of g minus c over m multiplied by v dt. So the area that inside the blue circle is called as indefinite integral because the limits of the integration are not specified in this equation. The analytical solution can be obtained if the indefinite integral can be evaluated exactly in the equation form. So this is actually can be evaluated analytically into equation 4.8 by assuming v equal to 0 at t equal to 0. So the derivation process is shown elsewhere in the reference book of Numerical Methods for Engineering 7 edition that I will not show here. Okay, the important fact is that the exact solutions of many ODEs of practical importance are not available. So this is where we need numerical methods as an alternative for these cases. So one very important method that engineers develop to overcome this problem is linearization. Okay, figure 2 here showing the sequence of events in the application of ordinary differential equation for engineering problem solving. So in this case, a parachutist problem is derived from the physical law, which is Newton's second law. Okay, the F equal to ma is the Newton's second law. And it was used to develop an ODE describing the rate of change of velocity of a falling parachutist. And then by integrating this relationship, we obtain an equation to predict fall velocity as a function of time. So we have analytical solution and also numerical solution. Okay, a solution of an ordinary differential equation is a specific function of the independent variable and parameters that need to satisfy the original differential equation. So to understand this, let us see this example of y equal to negative 0.5x power of 4 plus 4x cubed and so on. So this is the original function, which is a fourth order polynomial. And then we differentiate that equation to get the differential equation, which is ODE. dy dx equal to negative 2x cubed plus 12x squared and so on. This second equation, or the differential equation, is also describing the behavior of the polynomial, but in a different manner from its original function. Okay, rather than explicitly representing the value of y for each value of x, like what has been done in the original function, but the differential or in the ODE function is giving the rate of change of y with respect to x, which is the slope of the function x. So here, figure 3, showing that both function and the derivative is plotted versus x. We have the original function and the derivative function plotted with respect to x. So notice how the zero value of derivative correspond to the flat or to the zero slope of the original function here. Okay, so the maximum absolute values of the derivative are at the ends of the interval where the slope of the functions are the greatest. Okay, so our main objective in the ordinary differential equation problem is to determine an original function when the differential equation is given. All right. So from previous, we have the dy dx function, or the ordinary differential equation. So to gain its original form, we can integrate that equation. Okay, the differential equation can be integrated to get its original function. All right. This equation, when integrated, we will get equation 4.11 here, which looks identical with the original function in equation 4.9, but with one notable exception or difference here, C. Okay, in the course of differentiating and integrating, we have lost the constant value of 1 from the original function. So C here is called as constant integration. All right. So the fact that C is an arbitrary constant, so it indicates that the solution is not unique. It can be anything. For example, here in figure 4, we have 6 possible different solutions for the integration. Okay. Therefore, to specify a solution completely for one particular ordinary differential equation, It is usually accompanied by an auxiliary condition. So when we have an ordinary function, it usually comes with auxiliary conditions. Okay, auxiliary conditions. So for first order ODE, the type of auxiliary condition is named as initial value. Alright, it is required to determine the constant and obtain a unit solution. So in example or in equation 4.10, that differential equation is accompanied by the initial condition which is x equal to 0 when y equal to 1. So when we substitute these values into the equation of the here, equation 4.11 here with the constant integration C, and then we substitute the initial condition given, then we can get value of C equal to 1, which is similar to the original function. Okay. Okay, figure here provides an overview of the numerical methods for solving an ordinary differential equations problem. There are two broad categories which dealing with the initial value problems, that is Runge-Kutta methods and multi-step methods. Alright, so our topic will begin with the Euler's method, which has a very straightforward graphical interpretations. And then two improved versions of Euler methods, which is Yun and midpoints method, we will develop using visual arguments. Okay, and then following that, we will look at the concept of Runge-Kutta, which consists of first and second order of Archi methods. Okay, so this is the main subtopic of our chapter, so which is Euler's method. For the learning outcomes at the end of this lecture, you should be able to develop Euler's method for solving ordinary differential equations or ODE, and then you should be able to determine how the step size affects the accuracy of a solution, and then derive Euler's formula from a Taylor series, and use Euler's method to solve certain civil engineering problems based on certain errors requirements. Okay, so what is Euler method? This topic is devoted to solve ordinary differential equations, which is ODE, of the form dy over dx. So it's the function here that we use is a derivative function, dy over dx. Previously, we used a numerical method to solve an equation which in the general form of new value equal to old value plus slope times by step size, which in mathematical forms like this. So according to this equation, the slope estimate of psi is used to extrapolate from an old value yi to a new value of yi plus 1 over a distance of h, step size. So this formula can be applied step by step to compute out into a future and hence trace out the trajectory of the solution. All one-step method can be expressed in this general form, which is yi plus 1 equal to yi plus slope times by h, with the only difference being the manner in which the slope is estimated. The simplest approach is to use the differential equation to estimate the slope in the form of derivative, first derivative. So in other words, the slope at the beginnings of the interval is taken as an approximation of the average slopes. So this approach is called as Euler method. And then the method followed by one-step methods that employ alternative slope estimates, resulting in more accurate predictions. So all these techniques are generally called as Runge-Kutta methods. The first derivative provides a direct estimate of the slope at xi. So from figure 7, we can see the location of xi, where the slope is actually equal to function of xi and yi. The slope psi is equal to function of xi and yi. Where the function is a differential equation evaluated at xi and yi. And then this estimate can be substituted back into equation 4.14 here, where all the general equation, yi plus 1 and so on, to get this equation which called as Euler's method equation, or the Euler-Cauchy or the point slope method. So the general equation for the Euler method is yi plus 1 equal to yi times, plus by function of xi and yi multiply by h, or the step size. A new value of I is predicted using the slope to extrapolate linearly over the step of size h. Okay. Okay, now we look at example 1 for Euler's method problem. So the question is, use Euler's method to numerically integrate the equation. So given the function here is dy over dx equal to negative 2x cubed plus 12x squared minus 20x plus 85. So it's actually the same equation from before. From x equal to 0 to x equal to 4 with a step of 0.5. So the initial conditions is given. It is very important to know the initial condition, which is x equal to 0 and y equal to 1. The exact solution is given by this equation. Okay, so you need to compare the exact solution and the numerical integration. By implementing the Euler's method, the general form for Euler method is yi plus 1, or the current y that we want to estimate, is equal to previous yi, plus with the function of xi and yi, or the slope in this case, multiplied by size of the step h. So it is informed here that the step size is 0.5. So use that 0.5 into the equation here, 0.5. And then the size of step, 0.5 also. And initial y is actually, initial x is equal to 0. Okay, initial x is equal to 0, where y equal to 1. So the slope estimate here is solving this equation by substituting all the value given, then we will get 8.5. Therefore, the general equation can become this one. Y 0.5 equal to 1.0 plus 8.5 multiplied by 0.5. So this is the h. This is the h. This is the slope. Okay. That is the value for estimation. While for the true value solution, x is equal to 0.5, we just use the original equation here and put all the values of x. And then calculate the error as a true error, as a true value divided by approximate value. True value minus approximate value divided by true value. Then we get the answer in percentage. Okay, for the second step, we change the value of x because the first one is 0.5, and then the second one plus 0.5, it becomes 1. So this equation becomes this when x equal to 1. So this one is from previous, plus with the function of f with 0.5 and 5.25 value from previous. So we get y1 equal to 5.875. Okay, so the y1 is here when x equal to 1.0. The true solution at x equal to 1 is 3. Yeah, we can see from the table. The true solution is 3 compared to the approximate value, which is 5.875. So the relative error is big, negative 95.8. And then repeat all the computation effort, and you can compare with the results provided in table 2 and figure 8. So here we have a true value of y, Euler value of y, which is determined from the calculation. And then the percent relative error from global and local. So what is the global relative error? Is global error is the total discrepancy due to past as well as present steps. Alright, while for local percent relative error is referring to the error occurred over a single step. So each step there are own error. So that is called as local error. So figure 8 here is the comparison between the true solution, which is black in color, and a numerical solutions using Euler methods for the integral of y bar equal to negative 2x and so on. That with the step size of 0.5. So note that although the computation captures the general trend, so the general trend is like this. Okay, that is the general trend. Of the true solution, the error is considerably. That means the error is still can be filled or significantly. As discussed in the next section, this error can be reduced by using smaller step size. So you need a smaller step size compared to 0.5. Next, we look at the error analysis for Euler's method. The numerical solutions of ODE involve two types of error, which is first is the truncation error or discretization caused by the nature of the techniques employed to approximate values of y. And then the second one is the round-off errors. So what is the truncation errors? It composed of two parts. The first is the local truncation error that results from application of the method in questions over a single step. And then the second one is a propagated truncation error that results from the approximations of produced during the previous steps. So the sum of the two is the total or global truncation error. How to gain this error? By deriving Euler's method directly from the Taylor series expansion. So from the general equations of the Euler method, and then we expand the function into a Taylor series. Okay, where this part O multiplied by h power of n plus 1 specifies that the local truncation error is proportional to the step size raised to the next n plus 1 power. So the truncation error in Euler's method is attributable to the remaining terms of Taylor series. So we have the general form for the true local truncation error equal to first derivative of the function, okay, divided by 2 multiplied by h square and so on. So that is the general form or general equation for the true local truncation error. For h that's sufficiently small, the errors in the terms in equation 4.17 here usually decrease as the order increase, and the result is often represented as this or this one, where this is called as approximate local truncation error. Okay, now we look at the example for Taylor series estimation for the Euler's error. Using equation 4.17 here, okay, 4.17, the general equation for the true error. Estimate the error of the first step of the equation below. Also use it to determine the error due to each higher order term of the Taylor series expansion. So we have the function of differential function here, dy over dx equal to negative 2x cubed plus 12x squared minus 20x plus 8.5. Actually, the similar equation from before. So for the solution, first of all, we have the general equation for the true error, which is equal to equation 4.19, where the first derivative here is equal to the derivation of this function. Alright, so we get the first derivative equal to negative 6x squared plus 24x minus 20, and the second derivative equal to negative 12x plus 24, and the third derivative equal to negative 12. We can omit the additional terms after this, the fourth derivatives and higher, from equation 419, because this particular case for the polynomial function, they are equal to 0. That's why we're not considering them. So, but it should be noted that for other function, for example, like a sinusoids or exponentials function, this would not be true. So we need to consider only this case, which is the polynomial function. It can be considered. It can not considered in the equations because they are equal to 0. For example, the error due to truncation of the second order term can be calculated as this. And then for the third order term, using the equation, the above equation, negative 12x plus 24 divided by 6. And for the fourth order terms, using this equation. So we are considering these three equations, right, from here. So these three results can be added together to yield the total truncation error. So this is the total truncation error, which is exactly the error that was incurred in the initial step of example 1. Okay, so note that ET2 is bigger than ET3 and bigger than ET4, which supports the approximation represented in equation 4.18. So this is the equations of 4.18. Okay, as illustrated previously, the Taylor series provides a means of quantifying the error in Euler's method. However, there are limitations associated with its use for this purpose. So the first one is the Taylor series provide only an estimate of the local truncation. That is the error created during single step of the method. It does not provide any propagated or a global truncation error. And then the second one, the actual problems we usually deal with the function that are more complicated than simple polynomial. So previously we are dealing with polynomials, so it's quite easy. But for the derivative that are needed to evaluate the Taylor series expansion, other than the like simple polynomials, would not always be easy. Okay, it's quite hard. And then some useful conclusion that we can gain here. The error can be reduced by decreasing the step size, which is h. And then the method will provide error-free predictions if the underlying function, that is the solution of the differential equation, is linear. So if it's linear, then it's quite easy compared to non-linear. This latter conclusion makes intuitive sense because Euler's method uses straight line segment. Okay, so straight line segments to approximate the solutions. It is referred as first order methods. Okay, now let us see the example which show the effect of the reduced step size on Euler's method. So we need to repeat the computation of example 1, which h equal to 0.5, but this time we need to use a step size of 0.25. So after recalculating the example 1, so we get figure 9 here. The left one is a comparison of two numerical solutions with Euler's method using step size of 0.5 and 0.25. Okay. And B is the comparison of true and estimated local truncation error for the case where the step size is 0.5. Okay, so this is taken when step equal to 0.5. Note that the estimated error is based on equation 4.23. So which is the equation 4.23 here? Okay. Right. So for the solution, the computation is repeated and results are compiled in figure 9a. So here the figure, halving the step size reduced the absolute value of the average global error of 40%, and absolute value of the local is equal to 6.4%. This compared to global and local errors, for example 1 is 90 and 80, 24.8 respectively. Thus, as expected, the local error is quartered and the global error is halved. Alright. Okay, the effect of further step size reduction on the global truncation error of Euler method is illustrated in figure 10. So here is the figure 10. Notice that even when h is reduced to 0.0001, okay, the error still exceeds 0.1% because the steps correspond to 5,000 steps to proceed from x to y. Okay. Okay, here the plot suggests that a first order technique such as Euler's method demands great computational effort to obtain acceptable levels. Okay. However, it should be noted that despite its inefficiency, the simplicity of Euler method makes it an extremely attractive option for many engineering problems. So people are like to this method because it is very easy to program, the technique particularly useful for quick analysis. Okay, for further exercise, you can do the example 4 for Euler's method, where a polluted lake has an initial concentration of bacteria of 10 power 7 parts per meter cube, while the acceptable level is only 5 times by 10 power of 6 parts of meter cube. The concentration of the bacteria will reduce as water enters the lake. The differential equation that governs the concentration C of the pollutant as a function of time is given by dc dt, or the differential equation, plus 0.06 C equal to 0. Alright, using Euler's method and step size of 3.5 weeks, find the concentration of the pollutants after 7 weeks. Okay. You can do this at your home or at your room. And as usual, if you have any problems, just contact me via WhatsApp or here in Teams. Alright.